This video will introduce the two common modes of simple antennas, series resonant mode and parallel resonant mode, explore the feed point impedance characteristic of both modes on a Cartesian graph, explore the Smith chart presentation of the feed point of both modes, identify the Smith chart signature of both modes, and show the effective feed line transformation of both modes. There are two broad types of simple antennas, series resonant mode and parallel resonant mode. An antenna in the region of series resonance has a basic feed point impedance that comprises low resistance R that changes relatively slowly with frequency, and zero reactance X at resonance, and X changes relatively rapidly, positive with frequency. Examples include base-fed quarter wave ground plane and centre-fed half-wave dipole. An antenna in the region of parallel resonance has a basic feed point impedance that comprises very high resistance R that peaks at resonance and changes with frequency above and below resonance, and zero reactance X at resonance, and X changes relatively rapidly, negatively with frequency. Examples include a base-fed half-wave vertical and a centre-fed full-wave dipole. For this discussion, an NEC 4.2 model of a 1 metre base-fed vertical over perfect earth conductor is used. The chart shows the resistance and reactance components at the base of this antenna over quite a wide frequency range, and it exhibits three resonance. So to assist in exploring this, I've created a SimSmith or SimNEC model sourced from the data from the NEC run. So it's been imported as a file here into SimNEC. I've inserted a model of an ideal transformer. At the moment it's 1-to-1. I can specify the number of turns of the primary and secondary. I've inserted a section of transmission line which at the moment is 0 length. So these are having no effect. And what we're seeing is the R and X plots that are the same as what we got directly from the NEC model N4NEC 2. There are three resonances, and the resonances are where the reactance crosses 0, and it crosses 0 here at about 72 megs. It crosses 0 again at about 136 megs, and it crosses 0 again around 220 megs. So the first and the third of those are series resonances because the resistance is low. The second of them is a parallel resonance because it's very high resistance associated with the zero crossing of X. Now, when we look at that on a Smith chart, we see this spiral. And that's really informative. Well, I hope it is to you at the end of the video. So here's the first of the resonances at 72 megs. So the points go around this clockwise for increasing frequency, and it's clockwise not with respect to the centre of the chart, clockwise with respect to any arc section. So if you take an arc section here, the centre of that is somewhere down here, and the points progress with frequency clockwise around an arc centre. So there's our first resonance. The second resonance is up here, that's the high impedance or the parallel resonance, and the next series resonance is where the antenna is 3/4 wave in length, and that's down here. So that's interesting. Let's just insert a little bit of transmission line and look at what the effect is on that pattern. I'll just insert a very small amount, so 100 millimeters. I didn't see any effect because we're looking at the output of the transformer. Let's add in now the output from the transmission line, and you'll see what's happened to it. You see it's rotated clockwise. So at this point has rotated around to here about the centre of the chart. And if I increase this length, you'll see it rotate some more. Now I'm going to redo that. So that's the output of the transformer. Let's look at the output of the coax. Okay, this is the next section to insert. We're looking at the output of the transformer here, the magenta coloured trace. Let's look at the output of the line section. Well, it's overlaid it. It's the same because the line section is 0 in length. I'll turn off the transformer because what I want to do is add in a very small quantity of transmission line and increase it, and you can watch that pattern. Can you see that rotating? Look at the X up here. That's the high frequency end, and that's going to get the most rotation because that's where the electrical wavelength, the electrical length is increasing most. So we've been looking at the output of the one-to-one transformer with the magenta trace. I will now focus on the output of the transmission line. So we'll enable that. It's of 0 length. So when we enable the trace, it overlays the magenta trace. I'll turn the magenta one off so the chart's not confusing. And I'll insert a small length of this, just 50 millimeters. So if you watch the green trace, it's moved. So this point here has rotated circularly about the centre. Let's increase that length and you can just watch the chart rotate. Now, it rotates more at the high frequency end than the low frequency end. So what you'll see happening is the loop shape is changing. And it might not be terribly obvious where it started. So if I go far enough, you get some quite different patterns. This is all caused by rotation. In this case, the rotation is just over 90 degrees at 70 megs, but at the top end of this sweep, it's more like 270 plus degrees, 300 odd degrees. Let's return this to 0. So the thing that we've seen is that inserting transmission line, that is when you measure looking into a transmission line, the transmission line has the effect of rotating at each point on the locus there about the centre, but the rotation is frequency dependent because it depends upon the electrical length of the transmission line at the frequency where that measurement point was taken. So we've seen the sweep from 60 odd to 220 megs of this 1 metre vertical, and it's shown there in that circular plot. Let's focus in on a smaller part around the first series resonance. So I'll switch the sweep here to only focus on this part of the curve. Now, the key things to note here, it's shaped a bit like a letter C, canted forward a little bit. In this case, it's to the left of the centre of the chart because the quarter wave resonance gives a feed point impedance around 35 ohms. So it's going to be left. Sometimes series resonances might be over this side of the chart centre to the right. So for instance, a half-wave dipole would appear displaced to the right. Now I want to look at what happens again if we insert some transmission line here. I'll put in 0.1 meters, and as we saw in the bigger example of the spiral, but it's a bit clearer here, it's rotated around the center of the chart. And as we increase that transmission line, you'll see that rotate. So starting from the position where you see the kind of letter C, go back to that, kind of like a C shape, either on this side or perhaps on that side of the 50 ohm centre, that looking at it through transmission line rotates the locus of the points. And if you look at a scan that you see with the curve rotated like that, you can form the view that's quite probably the transformation, the results of looking through some length of transmission line. So this arc is a signature, if you like, of the series resonance, but it can be rotated and appear in a different orientation in angular terms on the Smith chart. Now, about this rotation, one of the things to remember is that for every 1 degree that we add of transmission line, it rotates the pattern on here by 2 degrees, because there's a go and return propagation delay on the transmission line. So, for instance, if I bump this up here to 90 degrees, you'll see it's gone around 180 degrees on the chart. So that's something to keep in mind in interpreting the chart and trying to relate the chart to measurements and transmission line that might be interposed between the measurement point and the device under test. So let's return to the wide frequency sweep of our test antenna. This was from 60 megs up to about 220 megs, and we'll focus this time on the high impedance resonance over here. And I've put the frequency in there as 136.4 by locating that zero crossing. I'll narrow the frequency range up to just look at the arc just in the small region. It makes it clearer to see what's happening. So here's a sweep from 120 to 150 megs, and we have a fairly shallow arc way out on the 50 ohm Smith chart. Now again, we can insert transmission line, and that will cause some rotation of that. So if you watch it a bit more, rotates more. If we took that up to 90 degrees, here it is right over here, halfway around the chart, 90 degrees, moves 180 around the chart. Now, that's not a very useful impedance there either. So 2 ohms, it's not very useful. This is inserting a section of 50 ohm line. What about if we inserted some different sort of line? Let's try 300 and see what happens there. It's different. Now we said before when we were using 50 ohm line that the 50 ohm line causes rotation about the chart centre. It causes rotation about the 50 ohm centre. Okay, so what we're talking about now is 300 ohm line. We need to adjust the chart reference to 300. And now you'll see that that rotation, I'll go back to zero length. So the rotation is about the chart centre. And if I just put 90 degrees in there, that takes us all the way back over here. And that's interesting. This impedance is looking more interesting. That's looking like 70 ohms. By adjusting the ZO, we can move this in and out. Go back to a 50 ohm reference, you'll realise that it's not rotating about the chart centre, but it's rotating about 300 ohms, which is just over here. And it's not so easy to see geometrically when it's not the chart centre. So now let's dial this ZO down and see what it does to this stuff here. Ooh, look at that. We've been able to match it to 50 ohms with a 90-degree length of 250 ohm transmission line. This is the basis of the once very popular end-fed ZEP. Was it a quarter wave of transmission line, and this antenna is a vertical half wave over a perfectly conducting earth. It's not the same as a horizontal half wave above ground, but there's the matching concept. Just the impedance of the line for optimal result may be quite different. So again, series transmission line rotates about the 300 ohm centre. If we're using 300 ohm, rotates about the 250 ohm centre if we're using 250. Here I've left the chart at 250. Now realise the reason why we need to use 250 ohms to get the proper rotation is because using this correctly calculates the reflection coefficient magnitude. So this value here, the reflection coefficient, is 0.665 and 180. If we take the transmission line out, the reflection coefficient of here is 0.674. It's approximately the same, but just about the accuracy of my clicking the asterisk on there, at about 0 degrees. So the chart only works in rotation when the reference impedance matches the transmission line ZO. So enough of that. There's your explanation of how a end-fed ZEP matching system works. I'll restore the chart to 50 ohms as a reference, and you'll see that here it is here matched up to 50 ohms. The SWR is 1.0 nothing to 1. Bit of interesting application of the Smith chart. Let's remove the transmission line. I'll change that back to 0. Another common method that's used for transforming it is with a transformer. Now this element F1 is an ideal transformer, and I can set the turns ratios. So let's increase the turns ratio. And you see what that's doing. That's just dividing the impedance by the ideal impedance ratio, and so it's just moving it left on the 50 ohm chart here. And we can get quite close to a 50 ohm match. So 3 turns to 15, so 5 to 1 transformer, or 1 to 5, whichever direction you look. And the SWR comes down quite low. This transformer is modelled as an ideal transformer. It's lossless and it's a broadband ideal transformer. Real transformers aren't that good. You'll get a slightly different effect. And keep in mind, this is again a lossless half wave over a perfectly conducting earth. So, in summary, we've looked at 2 different ways of matching this half wave, the end-fed ZEP concept and the broadband transformer close to ideal. And so we'll restore this transformer to 1:1, and there's the signature of a high impedance resonance. If we look at it in R and X terms, there's our peak in R. It's a bit jaggy because there's only a limited number of scan points in the model. But there's your peak in R at the point where X goes through 0. And if I was to turn on a SWR plot, so you can see the SWR of the bare or the native end-fed half wave is 26 to 1 in terms of 50 ohms. But we were able to transform that down with the broadband transformer and get quite a respectable looking VSWR curve. Again, the jag is the result of a limited number of scan points and the interpolation between them.